started recording if I'm not wrong. Okay. Hi everyone, I'm Sunaina and this is Projective Geo Lecture Part 2. Let me share the screen. 1 second. No, I haven't shared my screen. I'm starting right now. Do let me know if you can see my screen. Can you guys see it?
Yeah.
Okay. So, as usual, I said this in the last class also, but I'll repeat the same thing. Oh, also this is part 2. Although this class is essentially based on projectives, your elementary solutions are really appreciated here. So like, if you guys have an elementary solution, feel free to share it. And yeah, I personally have never solved a geo problem using any of the advanced techniques in a real contest except Sharigan and Nigel. So yeah, basically elementary solutions which are like angles, POPs, or even length chase. We usually prefer that. So yeah, hence to elementary techniques. Moreover, if you have like any feedback, just tell it and also interact and ask the doubts anytime. Also, I might have tech glitches, so like please bear with me if I get one. Yeah. So since this was part 2, we have let's revise what we did in part 1. In part 1 of the class, we defined what's point at infinity. We defined cross ratios for four points which are collinear. And remember, cross ratios are defined like cross ratios for 4 points ABCD is defined as CA by CB is to DA by DB. So that's is to is like the division symbol, but like we give this because it's kind of like the norm. And then we define the cross ratios for 4 points concyclic. So ABCD is like 4 points in a circle, and the cross ratios of ABCD is defined as CA by CB is to DA by DB plus minus, where it's plus if AB and CD, if the segments AB and CD do not intersect, and negative otherwise. We also, after this, did projections. There were basically 3 kind of projections. So one was line to line. Oops, somebody said. Oh yeah, go ahead, Arjit, if you have something to ask. Oh, it's okay. It's fine. Okay, so then we did projections last class. So this was line to line. Basically, the cross ratio of ACBD, which is ACBD, and the cross ratio of A dash, C dash, B dash, and D dash, the same. We proved it last class also. Next, we had this projection, which was circle to line and line to circle projection. For this, remember the perspective point must lie on the circle. So you have A dash, C dash, B dash, D dash, and P lying on a circle, and ACBD, 4 collinear points. And we get the cross ratio ABCD is equal to the cross ratio of A dash, B dash, C dash, and D dash. After this, we did the concurring chords lemma, which is like one of the best lemma. Just the proof is like one of the most beautiful proofs. Okay, I'm definitely exaggerating, but yeah, it's definitely a very nice lemma. So yeah, do remember it. Moreover, so I'll just repeat what the statement says. You have ABCD points lying on the circle in the same order. You have a point P inside the circle, and then you define EFGH as the intersection of PA with the circle, PB with the circle, PC with the circle, and PD with the circle. Then you get the cross ratios are preserved. So ACBD the cross ratio of ACBD is equal to the cross ratio of AGFH. Moreover, the P lying inside the circle isn't like a very big thing. You can also take it outside the circle. You just have to just make sure the intersections. Yeah. So after this, wait, everybody is fine with what we did. This was what we revised in the with what we did in the last class. After this, we defined harmonic bundle for four collinear points, which is just cross ratio is -1. The interesting property was if you have the cross ratio of ACBD -1, so -1, then that would imply that B and D are the inverted image of each other with respect to the circle with diameter AC and vice versa. Then we defined harmonic chords, which was basically circle. I don't know why I didn't write it over here, but uh, it's basically a cyclic quadrilateral which has the cross ratio of -1. Yeah, that is it. That is what we did in the last class. So I revised everything. Is there anyone who's having any doubts as of now? If I get to know, I'll move on.
Yes, ma'am.
Okay, I assume you have no doubts, Pranav. Okay, so today we'll first cover up. Oh, hold on. Do I have my net breaking or something? Or it's fine.
Oh, it's fine.
So today we'll prove three important lemmas, which are like very, 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 very to the power infinity useful in harmonic chase. The first is the Siva-Minelis lemma. The second is like I don't know the name of the lemma, but it's a quite well-known property of an harmonic chord, and it's like very useful. The third is the perpendicular angle bisector lemma. I won't be proving that because it's quite a tedious job to do so, but it's kind of similar to it's actually a polynomial circle, so you can just do the proof yourself if you want to. So these proofs, these lemmas would be given to you guys for as in problems, and we'll discuss the proof. So you guys will be given sufficient amount of time to try those lemmas. So here's the first lemma, which is called the Siva-Minelis, and it states that you have triangle ABC with concurrent savings AD, BE, and CF, the concurring at point X, by the way. Um, oh, oops. Yep. Then line EF meets BC at X, which can be point at infinity, it doesn't matter. Thing is, prove that X, the cross ratio of X DBC is -1. So prove that X DBC is in harmonic bundle. That's the first problem. Yeah. And if you guys are done with the first problem, then also comment when can X be the point at infinity. Is it fine if I give you guys like 5 minutes to try?
Shall I tell the proof, ma'am?
No, Pranav, you have already done it. Pehle se. Let's give people who haven't done it before a sufficient amount of time.
It is enough by some lunches then.
It's enough by some length chasing too.
I guess I have done it.
You have done it.
No. Why is length chase?
Sorry, sir.
What's
Sorry, sir. I will not lunches.
No, it's not length chase, no? He said length chase
this is
using
length?
Siva's and Menelau's theorem.
Yeah,
Yeah.
yeah. You can
No,
go now.
that's not the official, like, that's not the correct solution.
Okay,
That's
I'm not talking about the official one. So
I
don't be.
look not official, but like that's not the what do you say? Like neater way I meant.
Uh-huh. No, even
Okay.
even I know the length chase one day. I don't know the nicer ones. Okay, how about you share the nicer proof to us after we
Yeah,
get
sure.
the length chase solution?
Yeah, sure.
Okay, so I'll give you guys 5 minutes to try so that the people who haven't like done it can try it. The first thing is, uh, if you're like trying it for the first time, note that the name is called Seva Minilis and convert the harmonic bundle thingy to cross ratios and think about it. It's called Seva Minilis for a reason, right? Oh yeah. It's called Seva Minilis for a reason. Now think about it. How will you use Seva and how will you use Minilis? And when you get the two nice equations, what will you do? Is what I'll give as a hint. How about we yeah, how about we discuss at 7:20 p.m. If that's nice. 3 minutes to try. I agree. Which class did he share the proof by the way, Pranav?
Camp class we shared.
For Projective?
Yeah.
Oh, was I there in the class?
Yes.
Interesting.
Yeah. I thought you were gonna tell that proof, and like when he said the lenses, you were gonna say no.
I
Yeah.
okay, I literally okay, I probably forgot the proof. So
Yeah.
he's going to share the proof. Also, Aryan, are you done with the problem? If no, it would be better if you can try the problem instead of like asking Pranav. No worries, it's
Pranav, can you give some hint for the legend proof?
yeah.
Harmonic projections. Try to project the bundle which you want to prove harmonic.
Oh, okay. Okay.
Um, now I'm actually curious what's the proof. Are you sure you're like not confusing it with like another lemma?
Yeah, yeah.
Okay.
Like I also said length change that time, and RG said no, just no for length change.
Um,
That's why I remember.
okay. Okay, 1 minute to try, 1 minute left. So think about which which 3 points will you choose for Menelaus? Because Seva is obvious. Like you basically have like three savings concurring, so you have to apply Seva at like DFE with triangle ABC. So savings at AD, BE, and CF. You have to think how you're going to use Menelaus. Is it, and you obviously have to involve X because point X is not involved in salience. So you need to involve X. So it's either going to be cool the the collinear points XFE or it's going to be XPC or XTC or it's X. I don't know X. Let me think. So you have to just think about the Mendel's part. Should I discuss the proof, everyone? Like give the hint?
Oh, can you please let Pranav say his proof first? I'm really interested in his proof.
Listen the bad one first. The lens says that.
I'll share the bad one first and then the good one. Pranav will share. Is that fine? Huh. Okay, I'll give the walkthrough, and till then, Pranav can give the hint if he wants to. So other people can also see. Um, I don't know why it's not getting copied. Let's see. Oh, it got copied over. That's bad. Fine. Okay, so yeah, till then, Pranav, you can share your solution so other people can also like try the walkthrough one I shared.
Shall I just tell the proof you mean?
Yeah, go ahead. I have
Okay.
no problem.
Can you like scroll up to the diagram?
Sure.
Okay. Define this point AD cap FE as a T.
Mhm.
We have BCDX, the harmonic bundle BCDX.
It's you have to prove that it's harmonic bundle.
Yeah. So like
So
harmonic bundle BCDX equal to,
BCDX is equal to
if you project from A, this is equal to
X
F. No. F. No.
F, yeah, F E
F E and then
T
T
X.
X.
Yeah, you have to
And now if
show.
you And now if you project back from W,
Okay.
then F goes to C,
F goes to C. Ah, okay.
E goes to B,
E goes to. Dang. Okay, I see. This is smart.
P goes to D, X goes to X. So now
And
BCDX equal to CBDX. It's
yes,
harmonic.
this is so smart. Remember, you're so smart. Not gonna lie. Also, by the way, if anybody is curious why we are done, just write the formulas of cross ratios and you will be done. Smart, Rohan. This is the other solution. This is like the. I think we. This is sort of similar to the butterfly theorem. Anyways, so here were the hints. There's a reason why it's called 7 Use save on ADBFC and use Minilis on XFE. And then you divide the products you get. I think I hope everybody has tried it enough. Hopefully, I'll just tell the proof. So first, we use Seva on AD, BE, and CF. We get AF into FB, BD into DC, and CE into EA equals to 1. And then we use Minilis on XFE. That's like XB into XC, CE into EA, and AF into FB as -1. And hence, you divide these two and you get BCDX equals to -1. Is that fine with everyone? I think this was what Anurag wanted to tell as his proof. Yeah. GG, good job. Oh, GG, whatever. The second is the well-known property of harmonic quadrilaterals. So I'll just get this one. and you give this problem a good try. Because actually, when I tried it for the first time, I couldn't get it, but then now looking back at it, it's actually very, very, very useful. But it uses something which is not that well known, but it's actually useful. That's what my hint is. Anyways, I'll repeat the statement. It says you have 3 points lying on the circle ABC. Then you define AA cap CC, which implies the tangency, the tangent from point A with respect to the circle omega, and tangent C with respect to the circle omega. It intersects at point P. Now PB cap omega is D. Prove that ABCD is an harmonic quadrilateral. Is a harmonic quadrilateral.
Can I tell? Is,
So
is the proof supposed to be like a kind of elegant type proof or a normal proof?
it's a normal proof.
Oh, I got okay.
Do you have a elegant proof?
I
It
think
is an
so.
elegant proof.
I think so.
Okay. Well, then Siddharth, is it? Sorry, what's a harmonic chord? Okay. Do you remember the cross ratios we defined for quadrilaters, like 4 points in a circle, Manoj? Which was, yeah, over here. Cross ratios for 4 points, which are concyclic, is defined like this. Plus minus CA by CB is to DA by DB. A harmonic chord is basically the 4 points having the cross ratio -1. Yeah, concyclic. Cool. So yeah, Siddharth, is it fine if you can like share your elegant proof like after I share the
Yeah,
normal Bakwas proof?
that's fine.
Okay, I'm giving you guys like good uh, 8 7ish minutes to try. So we'll discuss the proof at 7:35 p.m. Um, the first thing you should notice is you actually have already defined that point, but try defining the point. I have defined an extra point E in the diagram. Think why I have defined that point. Oh, okay. AA and CC is kind of very used in solutions, but AA is like the tangency line. So the line tangent to the circle omega at point A. Usually it's also thought as like the line having the point like containing AA. Both points are AA. So it's like slowly this it's becoming tangent thing. It's kind of sort of similar to how you do differentiation, but yeah. Anyways, basically they are the
I guess I have
tangents.
a new proof for this, but that is also from some projections and lectures.
Mhm. I see. Okay, we'll discuss at 7:35 p.m. If Siddharth's and your proof are like different, then the proof I share, you guys can also share it. Cool?
Okay.
Okay. The proof also involves sim-medians. So like if you remember how tangencies are sim-medians related, then try using sim-medians. And there's like a very, very, very good property of sim-medians, so use that. Like sim-medians and the lengths of the triangles. They're like quite related to each other. It's actually sort of like for the isogonal conjugates, but then since the semedian and the median, they're like isogonal lines, so that's sort of a corollary. But yeah, we'll actually discuss it at 7:35. So yeah. Hi Ravi. Currently we're doing this problem, so yeah, you can try it out. Mm. Should I share the proof right now? Okay, I'll get the walkthrough and you guys can then try again. Actually, I said whatever I needed to say. Here's the walkthrough. Oops. I even copy the walkthrough. So define the point E, which is AC cap PB, and then find symmedians. There would be like two symmedians thingy. And then you do the ratios, length ratios, which is like a very, very, very well-known properties of symmedian. So yeah, it's sort of like sides ratio and square thing. Then Pranav, you can wait, it was not Pranav, it was Sid. Sid, you can share your proof, elegant proof.
Yeah, like that circle to circle projection, if you do it at P,
Mm-hmm.
A and C will stay the same and B and D will swap.
So you're projecting from P to
From the circle to itself at P.
circle to itself. Hold on. So you have AC, BD, and you're projecting it from
P. Like from a circle onto another circle, onto the same circle. That
okay. Okay. So then that would imply that A goes to A, C goes to C. Yeah, that's such a nice proof.
There is one more proof.
There's oh my god, there's like so many proofs of this. How was I like not known? Okay, I'll get solution one.
Have you not read Otis harmonics like solution 5?
I never read that actually.
Ah, yes.
I just okay these days like for Otis, I don't really read the theory part. I just do the problems. Anyways, yeah, go ahead with your solution, Pranav.
ACBD equal to
ACPD equals to
after projecting from A, it becomes T E B D.
huh, but no, this is not. I'm not gonna write this. This is actually a lemma, which is we were going to do that after this. I'm not. Guys, ignore what Pranav said. He's spoiling for the other problem.
No, that's the nicer way to prove this problem. That's all.
I see.
Yeah.
Um, Anurag, you had another proof, right?
Sid and I have the same proof, coincidentally.
Ah, I see. Okay. Okay, I'll share the proof, which was actually, the classical proof, which is very old. I'll share that proof. Um, it's actually a good proof, not gonna lie. It covers the basics. And it's what I think this is the proof which is there in the Egmont book, if I'm not wrong. or no? No, this one was there in analogy, my bad. Anyways, so you define the point E, and then you note that BD is like the semimedian for both triangles ABC and ABC. Now the well-known property of semimedian is like you have triangle ABC and you have AK being the semimedian. Then we have AB by AC squared is equal to AK, BK by CK. Yeah. We use this fact, so we get BA squared by BC squared equals to AE by CE, and we get AD squared by DC squared equals to AE by BC. Hence, we get BA squared by BC squared equals to AD squared by DC squared, which implies BA by BC is equal to DA by DC, and hence you get the harmonic thing. This also sort of gives you BA into DC is equal to DA into BC. This is like the product of the opposite sides of the quadrilateral, of the cyclic quadrilateral. Whenever the cyclic quadrilateral satisfies this property, implies it's an harmonic quadrilateral. It's quite important. It's not that well known, but it's like very, very, very important because it's used in a lot of problems. At least the problems I have done, many of them use this property. So it's the proof like कोई problems नहीं solve करेंगे. हाँ, इसके बाद this like I think there are 3 problems at the end. All of them are from Sharikan. So I think it will take a bit of time to reach to the problems. Just one more lemma to go and then we'll be starting the contest problems hopefully. Anyways, here's the last problem and we'll be starting the contest problems soon. Oh, by the way, is the proof clear to everyone?
Yep.
Yes, ma'am.
Yeah, that was such a nice proof, Sid. Anyways.
I also had a nice proof which you didn't listen.
I didn't let you because we were literally gonna do the same thingy for here, and you're like
Yeah,
literally
like it's the proof
spoiling
for
it.
that problem. It's the proof for that.
No, you're not
It's
gonna
not even a
spoil it.
different lemma, no. Or is it?
It's not. It's a good projection thing, so I just
Yeah, so like just prove that with this projection. No, what's the
yeah.
issue?
Guys, ignore Pranav. Prove that PEBD is harmonic. It's very simple projection. Just yeah. I'll give you guys only 1 minute because it's just like one projection away. Also, they're like projections are like quite fun once you get the hang of it. They're like very, very, very fun to do. But in general, yeah, let me give some philosophy till you guys try it. In general, I have wait, okay, Ravi said BEDP is EBDP harmonic. Yeah, पूरा से. Oh, so how did
We can project to that old harmonic chord and just get
Mhm.
that.
Yeah, basically, so basically you're projecting the harmonic chord to the line. That's what Anurag said, right?
Yep.
Okay. Let me give the proof only, or yeah, I'll just give the walkthrough for the sake of completion. Oh, okay. Like nobody else gives walkthrough. This probably giving walkthrough is like, yeah, this was the proof with which Anurag said. So we already proved by the previous problem that ABCD is harmonic. In actually, ACBD the correct representation is harmonic. Now you project it from A to the line BD, which you can do because A is a point lying on the circle. Remember, okay, you can only project from a circle to a line and vice versa, provided the perspective point is on the circle. So you project it from A on the line BC. A goes to AA cap BD, which is P. Um, C goes to AE cap BD, which is E. B and D would lie on the same position, and you're done. Nice proof. Yeah, Pranam, do you have an extra magical proof for both the problem? You can give us. Imagine mentioning your name. Okay, Bolo, do you have a proof? BDEP is equal to BDAC is equal to
It's the same
BDP.
proof, like if you have ACBD
Yeah,
minus 1.
yeah,
Yeah,
the
but
same.
like for that time it was ACBD equal to PEBD, which is equal
Mm-hmm.
to CABD.
AC?
ACBD
Mm-hmm.
equal to PEBD
Mm-hmm.
equal to CABD. So ACCA
Yes,
gets switched. So
yes. I think I should actually mention this. Pranav's proof, which was basically ACBD. You're projecting it from A on BD, which becomes what does it become? Let's see, P E B D, which you can then project it from C on circle omega. P goes to C A B D. Yeah, that's Pranav's proof. Is everybody fine with what we have done till now? Hopefully. Okay. Yeah, there was one last problem. Okay, after this, I promised we have three contest problems um, to do. This is like the last problem. I'm pretty sure you guys will be able to do this soon. So yeah, we have ABCD a quadrilateral. Now define point P as AB cap BC, Q as AB cap BC, and R as the AC cap BD. So basically, you're forming the complete quadrilateral. Now you define the point X and Y, which is QR cap AB as X, QR cap DC as Y. Then prove that PX, the ratio PX AB is -1. I know might have taken out of bracket, but yeah. This is also like quite nice projection. Use 7 minimalist and you'll get a nice projection. And then you project it. So it's like only one projection and use 7 minimalist. Let me write the walkthrough actually. It's basically finding one harmonic bundle and then project it from a good point so that you get PXAB as harmonic.
It is just that only, ma.
Yeah. A PYDC is R PXAB, and that's PYCD. Cool. You just have to show PXAB, so yeah, get done. जिसने रवि भाई चैट पे मत लिखो, नहीं तो जिसने नहीं किया फिर उसे करने को नहीं मिलेगा. It's fine. Manoj probably also got it. So yeah, that's nice. I know Hindi, okay? I got 98 in Hindi, if I'm not wrong. Yeah, 10 का boards में. मेरी accent अच्छी है, बस मैं नहीं बोल पाती अच्छे से. I have good accent, actually. Yeah, so exactly what Ravi told us. I'll just copy paste the proof here because it's exactly same to what Ravi said. Yeah. So by Seva Minilis, remember PYDC is -1, and then you project from Q to the line AB and you get PXAB as -1. Everybody is fine with it, right? I hope everybody is.
Yes.
Yeah, okay. There's a perpendiculars and angle bisector lemma, which I'll just simply state it as I said earlier, but I won't prove it. So let me make a very nice triangle. We have, because I don't want to hurt other geometers' feelings. This is a triangle, a nice triangle ABC. Now this lemma says that you have the angle bisector. Let's make the angle bisector. It doesn't require making triangle ABC. Now I'm like realizing why I'm making a triangle. But it's useful. So I'll actually, it's better to introduce the triangle ABC. Yeah. You have this point D, and basically AD is the angle bisector of the angle BAC, and you have this. Let me take another color because I know. No, this doesn't look nice here. And you have EAD as the EAD is 90 degree. Then by the perpendicular angle bisector lemma, you'll have E, B, B, C as harmonic. Moreover, if you have EDBC as harmonic and you have BAC and you have AD being the angle bisector of BAC, then you'll also have EAD as 90 degree. Similarly, if you have EDBC as harmonic and you have angle EAD as 90 degree, then that would also imply that that AD is the angle bisector of BAC. So if you have two of the three conditions satisfying, then the third property would also satisfy. That is what it says. So you have perpendiculars, which looks like this. You have angle bisectors, then you will have harmonics. So these three are kind of related to each other. They're like very, very, very nice config. Okay. Now we have cute Sharigan geos. Because not gonna lie, if you go to the harder side of the Sharigan, it's basically classical geos to the best. Like it's one of the best source to practice classical geos. And by classical geos I mean configs, harmonics, inversion, and POP. They hardly have any lunches, but when I was in grade 8 and when I was in grade 8, there was a very nice minimalist cheese sharikan of that year. Right now I'm in 12. I gave 2022 when I was in 11. Utilized 2019 sharikan. That problem. Anyways, the first problem of sharikan. Yeah, love cats. Okay. So the problem is Let I be the incenter of the triangle ABC, K be the common point of the external bisector of BC with the angle A, and then uh, you you intersect the line KI with the external angle bisectors of B and C with points X and Y. Prove that the angle BAX is equal to angle CAY. Something like this. I don't want to spoil it for you guys because the problem has the diagram has a nice one. No, it's actually kind of like a big spoiler. Make your own diagram. It has a nice point, which would simplify the life. That's why. So, how about you guys try it for a good amount of time? You should have made for new people. I should have, yeah, true. Let me make here only. You have it's sort of like this only. I can use this diagram. Let me use it over here. So basically you have ABC triangle and then K as the common point. By the way, if you guys don't realize, then AE is definitely the angle bisector over here. AE is the angle bisector of the angle A, just because it's forming 90 degree. So yeah. Then we have the angle bisector. Then I need to introduce I. Let's join. This is E, this is X, and this is Y. Yeah, this is the diagram. Hopefully, it looks nice, but yeah, try it. Try reducing the case YB, try reducing the fact you have to show it's BAX equals to CAY. Try reducing into a projective geo thing condition. And in fact, we just saw angle bisectors and like angle bisectors and projective geo is like pretty nice. Can you join AX and AY? Sure, why not? Do you want me to extend or something? KIXY होगा ना? हाँ वो तुम्हें प्रूव करनी है रवि. Like you have to prove it. इसीलिए AI बाइसेक्ट करेगा. Yes, definitely. And वो प्रूव करनी है आपको. So उसको प्रूव करने के लिए what's sufficient?
Can I say?
Are you like done with the problem, Siddharth? Like you did it right now, you know the solution पहले.
Yeah. Oh, yeah. I think also Ravi is also done.
Oh, so वो AX center को introduce करके होगा. Yes, exactly. We'll introduce. Okay, yeah.
Oh, isn't this nicer by Barry?
पता था ना. You're like
Yes,
literally
it's-
spoiling. You're like literally spoiling people. Don't people who are like watching this are in the meet or like watching the recording. Don't do Barry ever, please.
You
It's
length bash Siva Menelaus. What do you expect people not to do?
Seva is like bacha types, okay? It's like bacha. You like yeah, lenchas. It's not a bash exactly. Bash is like okay. Let me define what's bash people. Bash
I
is
think we should continue with the class.
it's okay. Bash is basically doing something without knowing what's the intention, what's like going on in the solution. You're just literally doing it. Your Muirhead is a bash. Using Muirhead inequality is a bash. Doing Barry is a bash. But Lenches, you know what's the motive. Okay, I'm probably contradicting myself. But yeah. Either Siddharth or Ravi, do you guys want to like share your solution? I was supposed to oppose GeoBash. Yes, I am opposing GeoBash.
I have done it also by seeing some hints from Ravi.
Yeah, okay, nice. So either of you can like share your solution. Is that fine? Anybody who wants to share the solution can go ahead and share it. Let me just give the walkthrough. So basically, what Siddharth, Anurag, and Ravi did, we translated BAX and CAY to the condition, to the projective condition. Remember the angle bisectors perpendicular lemma? You wanted to show this. You want to show this. Oh, my bad. You want to show BAX equals to CAY, but you already have BAI equal to CAI. Let me use another color. So it's enough to show that XAI is equal to YAI. Now, since you want to show this condition, it is sufficient enough and you already have KAI to be 90. It's enough to show KIXY to be harmonic. Now, how do you show that KIXY to be harmonic? Siddharth, do
Just
you?
map from the AX center.
Yes. So remember you have XB and you have YC and you have like external angle bisectors. So it's not a bad idea to introduce the IA, which is the external bisector. Remember, XB, AI, and YC would conquer at IA. Yeah. Then, Anurag or Siddharth or Ravi, do you guys want to continue?
Yes, yes.
Go ahead.
We already have that KBDCs and harmonic
Yes.
bundle, and
Yes.
we just project KBDC in to uh, what is it, KXIUI. Yes,
Yes.
so we're done.
Yeah, we're done. We're done because we got KIXY as the harmonic bundle, and that is what we wanted to show. GG, nice one. This was exactly the intentional proof. So let me just show the proof also. Yeah. Okay, why does it look like such a big proof, but then it was like only two
They
projections?
try to
Or
explain it. They try
yeah,
to explain the
they
idea
try
too.
to मतलब मैंने ही लिखा है proof. And
Oh,
sometimes like write
okay.
so big. Anyway, so yeah. Any doubts, anyone, with the proof? It was basically it's a very nice problem. And yeah. Basically IA and I are like really good at handling the angle bisectors and perpendicular lemma. Like literally they are very good with projections. So anybody, any doubts? I guess no. I think this okay, so this was from Sharigan 2022. I just don't remember the it was I think P90. Sharigan 2020-2022 P90. Like really, I don't know why it's like P19. It's not that hard, but okay, their choice. Here's another Sharigan 2022 problem. Sharigan 2022 problem. And I actually already spoiled it from you guys, but if you paid enough attention in the class, then it's spoiled. So basically, you have the products, you have a cyclic quadrilateral ABCD, and the products of the opposite side lengths of the cyclic quadrilateral, they're equal. Now you take the reflection of B dash, take the reflection of B over the line AC, and you have to show that the circle passing through AB, AB dash D touches AC. I just said the problem statement. Should I make the diagram?
So
Or,
by touches you mean tangent.
yeah, touches, yeah.
Okay, okay.
Mhm. I'm not okay. For 1 minute, think what the first statement implies.
It does implies that it is a harmonic chord.
Yes, it does. ABCD is an harmonic quadrilateral. We just did this. I mean, I said this. We did it in the last class itself. But let's see where I said it. Yep, yep. Let me see if I can use a nice color. Yeah. Okay, this looks a bit dark, but yeah. Implies ACBD is harmonic. Good job, Anurag. Hmm, yeah. Now you have a harmonic quadrilateral, so that's obviously cyclic, and you're now trying to reflect it. You're reflecting one point over this line AC. And now you're saying prove that the circle uh, passes through this. AB dash T. It touches the line AC. It's actually a pretty hard problem, not gonna lie. Like I took 1 hour to solve this. No, not 1 hour.
Oh,
Actually,
maybe can I share some idea?
yeah, you go ahead.
So we have that AB dash B has to touch AC, so it makes sense that it will be tangent at the point A. So
Mm.
we need to avoid configuration issues. I will try to use directed angles. We have directed angle of CAD is equal to directed angle of DB dash A. If we want to prove its tendency,
Mm-hmm.
then I want to somehow input something else like perpendicular bisector lemma.
Mm-hmm. Perpendicular. I see. How would I make the diagram for you? Also, now let's
I made, but you can make it. It will be way beautiful than what I have done.
I won't make it. I'll just give you guys. Actually, yeah. Let's. Okay. Should I spoil it, or you guys really want to try it? Like,
I give some time to try.
yeah, I'll give you guys like 5 minutes to think about it. You there's like a circle you want to like touch it. What am I saying? Okay, so there's like a circle which is tangent to the side. It's sort of related to a very nice configuration. Actually, this is a configuration geo. Like, if you know that configuration, if you know about that configuration, you're like done. Immediately done. That's my hint. Like, it's a very nice configuration. In fact, Atul was like, oh, this is like a well known property of that configuration. वैसे D को reflect कर सकते करो very shocking with that. Do you want me to reflect? Like, should I make a diagram and then explain? Okay, how about you guys actually try it nicely till 8:10 p.m. and then I saw my yoga. Yes, that is so true, Ravi. That's yeah, yeah. This is actually you're going in the right direction. Sort of. Yeah. Don't think about B only. No? Like don't think about D. Go to B. You're reflecting it. Then what would be B dash? Since you guys are in the correct direction, should I give the diagram? If I give the diagram, you guys will be like spoiled.
10 days we have to late and
Yeah, 8:10. Okay. Also, hi, Kritat.
hi.
Like, it's gonna be isogonal, which is true. So also remember symmedians and medians are isogonal. So and then you have like tangents, two circles, tangent. I gave enough hints. Now if I give more, you guys will be angry since I'm spoiling it. Think about it. Bingo! Oh my god, you're done. Yeah, Ravi, that's so true. Yeah. ECD okay. Yeah. Am I allowed to spoil now? It's not no actually Ravi I literally like wrote in the chat. Yeah, now I'm allowed to spoil. I'm sorry people. I was just so eager to like give the diagram because it's such a nice diagram. Ta-da! Can you see? Yeah, you guys can. I redefined everything. It's like a lemma. Now the lemma says if you have ABDC harmonic, you basically have I don't like this color. This color is bakwas. A D B C harmonic. Now you reflect D over the line BC, so it's HA. Yeah, prove that this point is the Humpty point. And to the people who don't know what are Humpty points, Humpty point is the point which lies on the median. So here it's the A median, and then it satisfies that AHA, oops, yeah, AHA, B, and AHA, C, these two circles are tangent to line BC. Anybody who wants to prove this lemma, Ravi, since you already did, would you like to prove this? Or Siddharth, oh wait, Anurag, anyone? Acha, tangent wala. Oh wait, this was not what you said or what? I mean, you guessed Humpty, so it had you like that. Yeah, I gave you the lemma. Prove this lemma, everyone. So you basically have to prove that AHAC is tangent to BC, and the other way also follows similarly. So prove that AHAC is tangent to BC. Isogonal conjugates. Hmm. It's simple angle chase. Mm.
Oh, can I say?
Yeah, go ahead, Siddharth.
AD is the median, AHA is the median. So then, like BAD is equal to CAHA, and BAD
Mm-hmm.
is equal to BCD.
Mm-hmm.
So then HACB is equal to HAAD, AC, I mean.
Okay. Should I write it? What you're saying?
Yeah, like it's like you basically written all the angles are equal on the diagram.
Yeah, I did. I'll wait up for some more time if that's fine with other people. Okay, so it's basically what like Siddharth only says. So I'll just write Siddharth's proof. Basically, he's like defining HA to be a point, to be the Humpty point, and then he says the reflection is like in the circle ABC. So since um so first, okay, I think this is how you prove it, but it's kind of like a very well known, but you guys can also try it on your own. Can anybody show why BHAC is like 180 minus angle A? Anybody? Like Siddharth's proof is a bit different, but yeah. Anybody who's up?
You can prove it just by reflections.
Yeah, like forget about D. Now I'm like saying you have ABC and then you have the Humpty point HA. Now prove that angle BHAC is 180 minus A.
It follows from tangency, right?
Yes, it does. So do you guys remember how we defined the Humpty point? So we defined it as the point where it's the point where the such that AHAB and AHAC they are tangent to the line BC. Now, if you guys remember, it's a very famous lemma. When you have like a circle, you have. Okay, I'll actually show it over here. So this implies that angle HAAC is equal to angle HACB, and you have angle HAAB is equal to angle HABC. Is everybody fine with what we said? And hence, but then you just subtract it, you get BHAC as 180 minus A. Yeah. Everybody fine with this?
Yeah.
Okay.
Is there any other problem to try?
Is there is. Are you like done with this problems, Anurag?
Yeah.
Okay. Okay, then I'll quickly finish it up and give the last problem. So now can you guys prove? So now you define the reflection of HA over BC. That's define it as D. Now you get that D belongs to the circle ABC. And now, as Siddharth said, since HA lies on the median, you get by angle chasing, you get angle HAAC is equal to angle HACB, which is equal to BCD by reflection, and that is equal to angle A, that is equal to angle BAD. And that implies that AD is DC median. So we are done by this. So we did this lemma. Now we have to prove the actual thing, which is basically the same thing. Anurag, would you like to complete the proof? Since you're done, would you like to complete the proof? I'll give the diagram for reference. This is the diagram. Basically, redefine everything and you're done actually. So I think everybody is clear with this, right? Clear with this proof? Okay, next problem. I'll give the proof for the completion so that the people who probably thought this was fast, they can look at it. We basically did the same thing. We got ACBD's harmonic, then what Sid said, we did that, and then just redefine everything and you're done. Okay, next problem. It's probably hard. It's like very hard. So like I'll give you guys good 5 minutes to try. Yeah. It's another Sharigan. It's from 2013 Sharigan. And it's like a very nice problem. Kia Ravi. Oh, okay, nice.
I think we cannot bash this, sadly.
Why is Pranav the meeting owner? I should have made the meet.
I think
I
there is
said
no
we
one to
cannot.
oppose Bash today.
Sorry, Anurag.
I think there is no one to oppose Bash today. So let him bash.
I said we cannot bash.
हाँ तो
Come on,
बाकी समय you're then thinking that you can bash.
no, no.
भाई यार आज
And
जाएगा
your
तो
person's lens
तब
is,
भी
you
मत
can see
बोलो
that.
please. Yeah, Ravi, if you like somehow remember the proof, then also don't tell. Is what Anurag telling. Yeah, it's a very nice problem. The perspective point is also very nice. But think about it. I'm not going to make a diagram. Do you guys want me to make a diagram?
Yes, ma'am.
Let me see if
We need
my
an aesthetically pleasing diagram.
yeah. True, we need an aesthetically pleasing diagram. Also, to the people who don't know, oh, my diagram doesn't include any nice new points. Yeah. Except one new point. Okay, I'll wait till you guys introduce that point and then I'll add the diagram. Is that fine with everyone? There's like one new point to
Can
be
you make
added.
this rough diagram till now? I have not even made the diagram.
Sad. Fine. Let's make a nice diagram. Okay, hold on. Let me check this diagram. Proof, whatever. Okay, yeah. So we have AD as the angle bisector. Do you want like a very nice diagram or any rough diagram works?
General icon as because
ठीक है. Why is this looking like a medium? Okay. This doesn't look like an angle bisector. Let's just make it look like a medium. Doesn't matter. Okay, this is the angle bisector. M and N are projections of. We have this as 90 degree. Not. Okay. This is M and this is N. And then you take the circle MN. So you this B point is so troubled. You're done? Simple tha. No, it's not simple. But okay, congratulations, Ravi. Okay, yeah, it's actually simple. If you get the point, the one which I wanted to introduce, then you're done. So that BAX equals to BAY. Yeah, let me make this line only. Yep. Yeah, this is the diagram, Anurag. I hope you're fine with it. I really don't know how people just remember the proofs of it, like proofs of any problem. Like until and unless like the problem is like super duper to the power infinitely good, I really don't remember proofs. But yeah. Ideas in general, I remember, but the solutions are like you need a very nice memory. But yeah. Anyway, so try it. Should I give like 3 to 4 more minutes to try? Okay, I'll give like 5 more minutes. The class would probably get extended. I'll give one hint now. Introduce a new point F, which is like very nice point. Which point? Since you um since you have to show that BAX is equal to CAY, remember the first contest problem we did? It's sort of similar to that. You want to show that BAX equals to CAY. You have the angle bisectors. So there's like a very nice point which you can add so that you get 90 degrees, and then it's reduced to showing harmonic stuffs. Is what I'll give as a hint. Think about it. Consider triangle AXY and the perpendicular. Which perpendicular, Anurag? Anyone else with any other ideas? Siddharth?
Like the external angle bisector at A
Bingo!
intersecting these.
So pro, Siddharth, so nice. Okay, yeah. Basically, now I can spoil the diagram. Can I add the diagram? I hope it's a nice diagram. Basically, what Siddharth said. Yay. So basically, what Siddharth said. Add the external angle bisector of A. Call and intersect it with BC. Call that point F. Yeah. So we did the first step. We're in the right track now. Oh, that's what Anurag wanted to say. I see. Nice. Now what do you have to do? What's the reduced condition, if there is any reduced condition? Can you like notice? Okay, go ahead.
I got a reduced condition, but I don't know if it's useful.
Okay, tell it.
If we project at like the point at infinity with respect to AF, then we get that ADMN is harmonic.
Yes, but usse pehle you like before that you get another projection, which is obvious. Basically, okay, fine. I'll just tell you what Siddharth said. Note that by the angle bisectors lemma and 90-degree lemma we have FD as -1, right? Yeah. And now everybody, as Siddharth pointed, AF is parallel to BM and that is parallel to CN because all three of these lines are perpendicular to the line AD. So remember how we defined point at infinity. AF at BM, they intersect at the point at infinity. Now, as Siddharth said, you will project it from the point at infinity, project the harmonic bundle FDBC, to the line MN.
Yes,
Actually,
then we can get a nice projection.
yeah,
And then
exactly.
just we can easily project to X and Y. So we are done.
Okay.
This
What's
was the first problem we did from point of infinity, didn't we?
yeah, it's actually the first point at infinity thing. Let me just write this. So this is ADMN, if I'm not wrong. Yeah, it is. Now, how do we end this? Anybody?
We need like MX, NY, and AF are collinear, or like concurrent.
Mm-hmm. We want what concurrent?
AF, MX, and NY. That would finish unless it's something easier.
MX. There is actually a simpler thing, like very simpler thing. You basically okay.
Can I tell what
Okay,
is
go
this?
ahead.
Yeah, we project from the point of infinity.
We already did. Okay, yes. Then
Okay. So we get that FDBC is equal to from the perspective of point of infinity FM uh, FNM. Can you
F.
see the diagram? Yes.
Yes.
Then we can get it to be FDMN.
FDMN.
Yes.
FDMN. How do you get that?
How we project X
So
to
wait.
M and Y to N.
Mm-hmm.
So we get that.
So
So through
so we get
similarity, we
what?
can
Wait. Hold on. What do we get? Anurag, I'm not getting that last thing.
I try to project B to M and Y to
Yeah.
N through
So
the
so
point
you
of
get
infinity.
ADMN as harmonic.
Yeah.
Yeah. And you have an MN thing.
Oh, then we just can easily get through power of one that dx by dy
Yeah.
dx into dy is equal to dm into dn.
Mm-hmm. Dx
So
into dy is equal to dm into dn.
yes,
Yes.
yes, yes. So we get dm by dx is equal to dn by dy.
Yes.
Oh, then we can just easily get that fx y is an harmonic bundle.
If x, y, c is the harmonic bundle.
Which
Let's
was
see.
just to be proven that fx y is an harmonic bundle.
What? Okay, fine. I see. Mm, Anybody
Can I tell?
else? Yeah, go ahead, Malay.
Yeah, we have ADMN is harmonic and we have angle MXN to be 90. So XM is the
Yes.
angle bisector of angle AXD. And
Yes.
similarly, we can prove that YM is the angle bisector of AYD and hence M is the incenter of triangle AXY.
Yes. Exactly. Yeah. Anybody has any doubts what Malay said?
It's
Should I
the
repeat?
more needed proof, I guess.
No, that's exactly what I had like a proof.
Okay.
Like, yeah. So yeah, I'll just repeat what happened here. I think. So first thing we did was introducing F, which is the A external angle bisector, the intersection with the BC. Note that this would be. Ooh, this color is so bad. Note that this angle FAD is 90 degree, and since we already have the angle bisector, by the angle bisector perpendicular lemma, we have FDBC is harmonic. Now then, as Siddharth said, we have AF, BM, and CN. They're like parallel to each other, so we project FDBC from the point at infinity to the line AD, and then F goes to A, B goes to M, C goes to N, and D stays the same. So then we get ADMN as harmonic, and then, as Malay said, we get since we have MYN as 90 degree, and we already have ADMN as harmonic, but again by the angle bisectors perpendicular lemma, we get that angle AYM is equal to MYT. Similarly, we can do the same over X, and we get AXM equals to MXT, and hence we get that M is the in center of AXY. And so we get, wait, where's my cursor? I lost my cursor. Okay, I got it. So we get this angle equals to this angle. And since we already have AD as the angle bisector, we get BAX equals to CAY. Yeah, this was the problem. We did 3 problems. This was from Sharik in 2013. I'm not sure what's the problem number, but yeah. Any doubts? I'll get a walkthrough right now if anybody's interested. I made such a colorful walkthrough, but then nobody saw it, so it's kind of like a waste if I don't share it. Yeah. This is the walkthrough. Yeah, with this that's all for today. 3 problems. Anybody any doubts? आपने प्रोजेक्टिव एग्मो से किया था या एबीजी? I actually did projective from EGMO. Yeah. Oh, you're asking Ravi. Sad. को ज़्यादा अच्छा नहीं एबीजी नहीं मेरे को एकदम पसंद नहीं आया. Like the Otis, I think the Otis one is like the best. The thing about projective geo is like the theory is quite less. The thing about projective geo is like theory is like quite less, but you'll get the hang of it only if you do like the problems and nothing else. With that, anybody has any doubt for whatever we did today? We did like 3 problems and then again some theory problems as problems. Anybody any doubts? If not, then yeah, I'll stop presenting. Yeah, that's all for today's class, everyone. I hope you guys enjoyed it. Thank you.
Thanks for the class.
Thank you.
Should I stop recording?
Yeah.